Good morning, everybody, and welcome back to Next Door NetAdmin. Last week, I talked a little bit about the various network classes, A, B, C, D, E, and I talked about the history of how we moved from classful networks to classless networks with CIDR. While I was talking about it, I used a couple of terms that I said were personal to me, the 0 address and the 255 address. I'm going to talk a little bit about what I mean by that today. And I'm also going to go into a few other things about various cast of characters, shall we say, of cast of traffic that we've got. But first, these addresses. A more technical way of referring to these addresses would be the all zeros address and the all ones address. All ones, what is this? 11.11.11.111? No. Remember that the purpose of the subnet mask, or the network mask, but subnet mask these days, is to distinguish between the network portion of an address and the device portion of an address. It does this in binary, where every position with a 1 indicates a part of the address that is the network or subnetwork portion, and everything with a 0 indicates this is the host part of the address, the device part. All right. So what do we have? Well, when you have the network where it's just the network bits and all the host bits are set to 0, that is the all zeros address. And you never use this in an actual network. Why? Because the devices routing into the network have no way of determining whether you are trying to address the network as a single block or whether you are addressing a device. So to avoid confusion, you just never use that address. The all ones address is similar, except that you have all of your 1 bits in the subnet mask. You have your host portion of the network. The all ones address is where every bit in the device range is set to 1. This is a special address called the broadcast address for the network. What's the difference here? Well, the difference is that by design, Ethernet is a bus architecture, or it started as a bus architecture, where everything connected to the same physical network segment, and they still connect to the same logical network segment. On the same logical segment, there's a lot of traffic going back and forth. Devices will only listen to and process traffic that is destined for their IP address. They might, depending on the architecture of the network, they might hear traffic that is bound for other IP addresses, but they will ignore it. They will simply drop it, not pay attention to it. It's not for them. The broadcast address, on the other hand, is meant for every device on that network. And so a broadcast, a packet sent to the broadcast address will intentionally reach and be processed by every device on the network. So because this is a special use address, again, you can't use it for a standard device, which is why you end up with always subtracting 2 IP addresses from however many addresses you think you should have, because you're allocating 1 to be removed for the all zeros address and 1 to be removed for the all ones address. If you have a full octet that is all ones, that's 255, which is why I've come to shorthand it as just the 0 address. It's the all zeros address. It's 0, okay. Or you have the all ones address, which I'm calling the 255 address. But it's important to note With CIDR, you could have something like a /28 network. Your 0 address and your 255 address, if that's the terminology we're using, will not necessarily be 0, and it will not necessarily be 255. I really should be saying all zeros and all ones. I really should, and I'll try to catch myself when I'm making videos in the future to use that more correct terminology. Because if you have a network like 192.168.64, if you have a /28 network, 64.64 is the 0 address for that. Even though the last octet isn't 0, it's .64. But if you look at the network portion, you'll see that the .64 in a /28 is in the network portion. So it is the all zeros address, but it is not 0. So calling it the 0 address is incorrect. And what would the 255 address be, the all ones address? Well, if you set every single bit in the host section to 1, that gives you 15 because you've got 4 bits. So when you actually look at 192.168.64.64, the 255 address is actually 192.168.64.79. That's not 255. If I call it the 255 address, that's wrong, but the all ones address is correct. So this is a place where my shorthand, my slang for this address is not correct. But you can see how it kind of led to me calling it that way, even though it's wrong. And I should do better. So, broadcast traffic, I've just mentioned. There are many other casts of traffic. The first one being unicast. Uni, 1. You send it to one IP address and one device receives that traffic. That's all unicast is. It's your standard, put an address on it, send it out. Cool. Let's detour for just a second here and point out that while I'm talking about IP addresses, and we'll continue to talk about IP addresses, unicast and broadcast is also a concept that applies to layer 2 networks and MAC addresses. In most layer 2 Ethernet networks, when you send to a single device, that is a unicast packet. You're sending to a single device. If you want to send a broadcast, you send it to an address that is all Fs, which is the same thing as in an IP network. If all of the bits in the MAC address are 1, that is a broadcast frame. And that is it frame? Yeah, Ethernet frames. Sorry, terminology review really quickly. If it's a broadcast frame, it goes to every device and it's processed by every device. In a switched network, switches have to deal with this differently. A switch doesn't know about where an individual MAC address is located until that device sends with its address in the from header. If it's going to a single device and the switch knows where it is, the switch will just send it to that one device. If it's to a device that the switch doesn't know where it is, it has to send it out every port except the port where it came in, because it's got to essentially flood the network, and we call it flooding, until the device that it's addressed for responds. And then the switch can say, I sent it out everywhere, but it's coming from port 5 over here. So future responses future traffic going to that MAC address just go out port 5. Okay. Broadcasts intentionally have to go everywhere. So when the switch receives traffic for the broadcast address, it floods the network. This can become a problem if you have devices that are connected in a loop. If the devices aren't smart enough to know that they should break that loop and just use it as a potential redundant pathway in the network, then you can get broadcasts traveling in a circle. And every time they hit a switch, the switch has to send it everywhere, and it just keeps on going in a loop. And this can lead to a condition that we call a broadcast storm, where there is a storm of traffic and it just keeps going until the traffic dies out. And it may not die out until somebody literally goes over there and pulls a link to break the loop and stop the traffic from circulating. Or if you can get to a switch that has a feature called storm control enabled, then at some level of traffic, it'll start dropping traffic and stop the loop from occurring and continuing to build. But in all cases, storm control is something that an admin needs to set up manually, because the admin is the one who knows what level of traffic is normal for a particular network. Because once it hits that threshold, everything is going to be stopped from there on by the switch. So if you have a high traffic network, maybe you need to set that threshold a little higher. If you have a low traffic network, maybe that should be lower. Storm control is not something that you can just blindly enable, or you really shouldn't. But that's how it functions. So unicast and broadcast traffic is something that can happen at layer 3 for IP addresses, or at layer 2 for MAC addresses on an Ethernet network. How about the others I mentioned? Class D networks are reserved for multicast traffic. Well, if unicast is one and broadcast is all, it's a logical inference to say that multicast is probably headed to multiple stations at the same time, and that would be correct. Multicast traffic is designed to be one sender that sends to multiple devices at the same time with a single packet of IP traffic. And so multicast addresses are reserved and registered for this for various purposes by internet spec, essentially. And it says this particular multicast address is reserved for all routers on a segment, or this one is reserved for all routers and all backup routers for something like OSPF. It will send its routing updates via multicast traffic. Multicast has a lot of challenges associated with it when you're talking about designing a network to deal with this, because how do you start receiving multicast traffic? Well, first, you may not have. Let's back that up for a second. You may not have the traffic on the link. Why not? Well, if every router on the internet forwarded every multicast stream, you would overload your network. It's intended for things like video streams or voice streams or other traffic that can be sent from a single source and reach multiple devices. Okay, fine. But if the multiple devices is everybody all the time, that's essentially a broadcast. And that's not how multicast is supposed to work. So routers will not start forwarding multicast traffic into a particular network for a particular stream until something tells them that they need to. The protocol that does this is IGMP. Internet Group Management Protocol. A device, an end station, first needs to find a route processor. It needs to register with its router and give it an IGMP join message saying, I want to join this multicast stream. Then the router needs to figure out, okay, who do I speak to upstream who's already receiving this, and needs to send a join message for that. And so a station has to join the multicast stream, and then the router needs to be able to inform switches along the way. Switches usually have a setting called IGMP snooping. They snoop on the join messages so that they know when multicast traffic for this particular address starts flowing through the switch. It doesn't need to be broadcasted across the entire network. The device on port 9 over here is the one that wants this multicast traffic, so it goes over there. And if somebody on port 12 also wants to join the same stream, okay, this stream is now going to ports 9 and 12. It's a very complicated set of protocols, and the setup for it is somewhat arcane. Not a lot of network admins have to deal with this. I do not usually have to deal with this. As bandwidth has gone up, in a lot of cases, it has become more economical and certainly easier for all of the network admins and network engineers along the way to deal with things as a series of unicast streams. Every time you're watching a live broadcast on YouTube, well, every person has their individualized stream from YouTube, even though it's a live broadcast. It's not a single, here is the packet at this time, it gets sent out. And if you miss it, you miss it. Because YouTube uses things like buffering. Your browsers also try to buffer. It tries to request enough traffic so that as bandwidth goes up and down and there are traffic jams and then it gets sorted out again, all behind the scenes, you just get one smooth, uninterrupted playback of your content. So because of that, different stations may buffer at different rates. And so for the most part, you're going to get a series of individual unicast streams going to each separate device that hits the web server, rather than a whole bunch of people trying to send multicast join messages to join a single stream of traffic that then has to go to different corners of the internet depending on who requested it. Multicast is a bit of a pain. And the last thing I mentioned was Anycast. In concept, Anycast is very similar to unicast. The difference is it might go to one of several different places. I'll give you an example. Google Public DNS is at the very well-known IP address of 8.8.8.8. Where is 8.8.8.8 located? It's not a single location. There's only one address, the second address being 8.8.4.4. But there's only one address, 8.8.8.8. But it's located in many different data centers around the world. Which one you go to is a function of which one is closest from a network perspective. So you can send to a single address and it looks like unicast, but behind the scenes, it's Anycast. It's going to whichever one of these locations that calls itself 8.8.8.8 is the closest from the perspective of the network. Why haven't we switched to using Anycast for everything? Because it's complicated. The main internet directory, shall we say, of IP addresses, the main routing table, which is handled by a protocol called BGP, it allows you to say, I can reach this target network through this path or through this path. This path has a cost associated with it of 10. This path has a cost of 100. It's a longer path, or it's more expensive transit, or what have you. It's all administrator defined. I should use the lower cost path first. Okay, but if I can't reach it through there for whatever reason and I stop hearing about it, then I have this backup path that I can use in this direction. So in order to make Anycast work, you have to be announcing that network, that address, from multiple locations on the internet, and then the routers will collectively just pick whichever one is closest, lowest cost, highest weight, lowest or highest priority, excuse me, and they'll sort that out individually. And we're talking the big routers, not your home router. Your home router typically does not see any of this complexity. We're talking your ISP's router. We're talking their ISP's router. The big guns, as it were. So Anycast can go to multiple locations. And it'll look like unicast. The response will come back. Cool. The other thing that you really need to be careful about with Anycast is the various locations may not be kept immediately in sync. So if you are talking to one server and suddenly that path drops out, your traffic to that endpoint will suddenly be going over to this version, and it may or may not know anything about what you were just talking about. If it doesn't, then you essentially have to start from scratch. For something like DNS, this is not, generally speaking, a big deal. You send a question, you get a response. The next question and you send and the next response you get may have nothing to do with your previous question and response, and they don't have to be linked. So that is a good choice for Anycast traffic. If you're talking about logging into a website and downloading files or getting a video stream, switching to a different source is going to be a little bit trickier. But even then, there are protocols that can help make this easier. And a site like YouTube almost definitely has its ways of dealing with this. I just don't know what they are because I don't work for YouTube. Ha! So that's kind of what I wanted to talk about today. Clearing up some of the unclear, vague language that I used last week, and then talking about the various casts of traffic. Multicast in particular, because multicast is really weird. And if you're ever wondering, what about the Class E networks that were reserved for use? They're still reserved. Are we going to see anything done with them? No, probably not. I don't think anybody would recognize them as a valid network for use in anything but in a research context or for testing, because that's what they were designed for. They're not live addresses. But the good news is that was the smallest class of networks, so it's not like we're missing out on anything. So, yeah, that's what I've got for you today. So, thank you very much for watching. I hope that was informative and or useful for you. I am your next door net admin, and we'll see you next time.